Okay. All right, so remember, a rational expression is really just a fraction of polynomials. And so we need to use both the things we know about fractions and the things we know about polynomials to be successful with these kinds of expressions. What we saw last week was if we have something like this is a kind of typical rational expression. We want to be able to do all of our operations with these rational expressions, and then eventually we want to learn to solve equations that involve rational expressions. And so when you look at this, the number one thing to do is to factor. So whenever we're working with rational expressions, no matter which operation or manipulation we're trying to do to it, it's always going to be better if we have a factored form. So I'm going to start both of these by factoring. The bottom, you'll see quite a lot of these difference of squares. They're nice because they're, you have to factor them, but they should go pretty quickly, right? Like once you see it, it factors immediately. Some of these other trinomials, they can make the problem kind of long and tricky if you have to spend, you know, some time and energy factoring those. So you'll see some of that, but usually nothing too challenging for the factoring here. And then once it's factored, right, then we can do and see what we need to with the problem. So with this one, and I guess I didn't give you good instructions here, but it would be a simplify. So when we simplify this, right, we cancel the x plus 3's because those are now common factors. And I'm left with x minus 6 over x minus 3. And what we saw last week is that if you simplify or multiply or divide, fundamentally this comes down to factoring and canceling. Depending on which of these, you know, if it's division, you have to multiply by the reciprocal, and if it's multiplication, you have like two pieces, but it doesn't fundamentally change the structure, which is just factoring and canceling. Okay, so if you've watched the videos, this is how I organize the thinking on this, on these problems. It's the same as what I do in the little videos, and it's because most of the time I find that students are able to do the work, but they mix up the kind of problem. So they try and do the wrong kind of work for the wrong kind of problem, right? So it's like they know how to do it, but they're just not sure how to apply it properly. And so I'm trying to give you some sort of rules or structure so that you know what kind of general approach to take. I find once students start taking the right kind of approach, by and large, they get the problem right. Right? Not always, we make little errors, but fundamentally they get the problem right. So this is one class of problems, right, that I like to group together. Simplify, multiply, or divide. We're just really factoring and canceling. So another class of problems is when you have to add or subtract rational expressions. Let's make that x squared minus 4. Okay, so here's an addition problem. And what we want to remember is our fractions. When we add fractions together, we have to have a common denominator in order to add them. Right? And so just like the last problem above, I do want to start by factoring. So I don't have to overthink that. Right? That's a difference of squares. This one has a common factor of 5. So I'm factoring. but I'm not trying to cancel, right? I'm not factoring just to cancel because this is an addition or subtraction problem. I'm factoring to create common denominators. So here we factor to create common denominators. And so what we do to create a common denominator is I have to introduce something new to this problem, right? So the previous problems, we didn't have to introduce anything new, but here to create a common denominator, I need something new. Here, I don't have a factor of 5 in the denominator, so I need to multiply top and bottom by 5, right, to create that or work towards that common denominator. And here I have a 5 and an x minus 2, but I need an x plus 2. Okay. So this is the very first and really important step. Now I've got the common denominator, so I can add these numerators together. But in order to do that, I need to multiply them all together. So the spot where I see students still make a mistake sometimes is they'll sort of start to combine these, but then they'll just be too tempted to like cancel these x plus 2's out. But you just put that x plus 2 in there to get a common denominator. So you don't want to cancel it out. You need to keep that. Multiply these numerators together, right? So 5 times 2 gives me 10. Here I get 3x plus 6. And what I like to do is just, keep track of the numerator. So like multiply it all out and add it all together and then put it over this common denominator. Just saves me a little bit of work so I don't have to recopy the denominator every time, right? These can turn into long problems if you write down every single step each time. Now at the end, I would like to simplify it if possible, but I can see that there's no common factor here, nothing that's common to reduce any of that. So that's as far as I can go. So it's a very different process, really, right? I mean, I am factoring, but I'm doing very different steps than I would have with something like this. And if you can keep that straight and show that you're creating common denominators, you're going to be well on your way towards getting full points or certainly partial points on any of these problems. Subtraction is almost the same, right? It's not fundamentally any different, but let me show you an example that's got another little complication in it. Let's try 2x over x squared plus x minus 6 minus 3 over 2x plus 6. I had to think about that to make sure I had the right pieces. So there's two things you should notice right away. I was going to say the first thing, but really it's a rational expression is one thing that you want to notice right away. And then the second thing is that it's subtraction, right? So that puts me right in this same ballpark, right, of the last problem that we did. Of course, that's obvious when we're doing this presentation because we always do the same kind of problems a couple times. But when you see them on a test or a quiz and they might not be in that same order, then it's important that you're able to recognize those so that you know how to approach the problem, right? So subtraction of rational expressions, I'm thinking common denominator, and I'm thinking factoring. So this is x plus 3 times x minus 2, and this is 3 over 2 x plus 3. It's not always true that there's a common factor here, but almost all the time. when there's not a common factor, it can be a pretty big and messy numerator. And so you'll find that when you have more complicated expressions like these, that when you factor them, there probably will be something in common that makes it simpler. So just like before, I want common denominators, and it's actually kind of similar in that there's just a constant that's needed over here, and there's a x minus 2 that's needed over here. No big difference here so far. The one thing I want to alert you to is that when you are subtracting, the subtraction is actually connected to the numerator here, which is 3. So really, when I do this problem, it is easiest, I think, to keep the negative with the 3 and then distribute that. So that's going to give me minus 3x, but then minus 3 times minus 2 is going to be a plus 6. Okay. So that's the watch out part with subtraction, is that if you have to distribute it, it's really easiest to do that in the beginning. It's not always possible. The other way to do it would be to distribute first, right? Multiply this out however you'd like, and then distribute the negative to both of those terms, right? But either way you do it, you've got to get the negative through the multiplication. It needs to be distributed. You can't just subtract the 3x. You've got to also subtract the negative 6. 4x minus 3x is x. And I've got to make sure to write that over the common denominator. Don't lose that denominator. So if you need to write it in each step, that's fine. If that's what it takes to not leave it behind, right? Your answer can't be just x plus 6. It's got to be x plus 6 over this expression. Any questions on either of those last two problems, this addition subtraction process? In some ways, I think it's probably the most difficult of the things that we do in this section, just because you have to change the problem, and then you've got to kind of continue and do some other work too. So it's not a sort of direct problem. You kind of have to work your way towards the answer, and those often make them a little harder. You got to hold those ideas in your head. Very capable of doing all of these steps. There's no actually really hard steps in here, but it's a couple different things all linked together, and that's what makes this a slightly challenging problem. Okay. So our last type here, or sort of big umbrella type of problem, is to solve an equation. It's a very different process than the last two processes. Should be very easy to recognize because it only applies when you have an equation, right? And neither of the other ones were dealing with equations. And in many ways, it's easier than adding or subtracting the fractions together. So our goal when we're solving equations is to eliminate the denominators by multiplying by the least LCD, the least common denominator. The goal here is that we don't actually want to work with the denominators. We want to get rid of the denominators. So here's an example. Let's try 24 over x squared plus 10 over x equals 1. So it's kind of a simpler version. There's no binomial pieces. There's just the x squared and the x. But it is a rational equation, right? And I see right away it's an equation. And I also see fractions, right? I don't even actually care what the denominators are. Anytime I have fractions, I want to eliminate those fractions, those denominators, by multiplying by the LCD. And this is something I tell my calculus students. Same strategy works. So it's just a general strategy for solving any kind of equation that has a fraction. It's going to be better off if you can get rid of the fractions. And so the way to do that is to multiply all the terms by the same thing. It's going to cancel all the denominators. You've got to make sure you multiply every piece, every term by the exact same thing. If you don't do that, then you've changed the equation and you're not going to get the right solutions. So I want to get rid of the x squared, so I'm going to multiply everything by x squared. And it turns out the x squared is going to also cancel with the x, right? So it turns out that x squared is actually the LCD. And what happens here, right, is that the x squared, my goal is to eliminate the denominator. So I don't actually want to multiply this together. I want to cancel it all out. So I end up with 24. Here, one of the x's cancel. Equals x squared. When you get rid of the denominators, you're going to get a nicer equation, one that we've seen before. This one is a quadratic. So I want to set it equal to 0 and solve. Sometimes they'll just be linear. And we can solve that one even more directly, but here got it equal to 0, so I want to factor this. If I did this right, x minus 12 and x plus 2 work. So x equals 12 and x equals minus 2. The only kind of unusual thing about this is that you could do all the work correct, but you could still get answers that don't work in the original problem. So when we do these problems, we have to go back to the original problem and check our answers. Now, luckily, you don't actually have to go all the way through and check that your answer really does make the equation true. Assuming you did all the work correct here, you just have to check to make sure that these numbers don't make the denominator 0. If they don't make the denominator 0, then they're going to work in your equation. The only problems you can get if you did the problem correctly was that you can get some answers that seem like they're answers. They would solve this, but they wouldn't solve the original because they would make one of the denominators 0, right? Which then would be undefined, couldn't work. So you want to check the answers. You can't make the denominator equal 0, right? That's what you're trying to avoid. I want you to recognize how different of a process it is, right? It's certainly related to our previous problems a little bit, but we're not trying to do the same things, right? We're not, we have very different goals, right? Our goal here is to find answers, numbers, not just to simplify. And our process, of course, is very different. I'm stuck with the denominators when I have a problem like this, right? They don't go away. I'm just able to change it or manipulate it a little bit, right? But here, because I have an equation, I'm able to change it by just multiplying on the top. So I don't have to multiply top and bottom. I can multiply both sides of the equation. And that's what allows me to do the canceling. Right? If I have to multiply on the top and bottom like these last problems, these adding or subtracting problems, then of course nothing actually cancels here, right? That's not my goal. My goal is to get common denominators. So that's sort of the part that you have to keep straight in your head. Let's see another example here of these equations. Let's try x over x squared minus 9 plus 2 over 5x plus 15 equals 3 over 5x minus 15. See what happens. So, as always, take a second, make sure you identify the type of problem properly, and think about your strategy. You don't want to just dive in on these and get yourself into the wrong spot. It's very hard to backtrack if you head down the wrong path. So you've got to get a good plan for starters. And the good plan that you should see is that this is an equation and it's got rational expressions. So my goal right away, I know what I'm trying to do is to get rid of these denominators. And I want to do that by factoring. So, right, we factor each of those pieces. And now I need to think about what's the common denominator, right? What factors give me, are common to all of these? Well, I need a least common denominator, right? So it's got to have an x minus 3 and an x plus 3, because that's here. And it also needs a 5. I already have the x plus 3, and then I already have the 5 and the x minus 3. So my LCD is 5x minus 3, x plus 3. That is what I'm going to multiply by each of these pieces. The way I like to do that is just write that here in the numerator. So 5x minus 3, x plus 3. 5x minus 3, x plus 3. I need to multiply every piece by the same thing, every factor. Or sorry, not every factor, every term, right? There's 3 big terms here. So all of them get multiplied by the same thing. Otherwise, I've messed up my equation. Now, what's great about this 5x minus 3x plus 3 is it's going to cancel a lot of these factors. So this is just going to leave me with a 5x. Here a 5 and an x plus 3 cancel. And here a 5 and an x minus 3 cancel. And it looks, well, it looks pretty terrible here, right? There's a lot of different expressions and factors and pieces, but almost all of them cancel, right? Or at least a lot of them cancel. And what I end up with here in the end is actually a pretty easy equation to solve. And it's just a linear equation. 7x minus 3x is going to be 4x. So if I add the 6, 4x equals 15 and x equals 15 fourths. Now remember, I am going to check my answer. So I look back at the original problem. It's actually easiest here to look at the factored form. That's the easiest way to see if any of these values make it 0. I would only have to avoid 3 and minus 3. Those are the only possible ones that make it 0. And of course, that's not 3 or minus 3. So I can leave that. And that is my answer. Questions? Anything? You guys feeling good?
We gotta go now, though.
Okay. I hope that's a good thing. There are some application problems, but they're similar. It should be similar to kind of what we've done before, in that you define your variable carefully and you set up your equation, and then your equation will just involve some rational expressions, right? So you'll need to solve that, right, using your techniques. But the setting up part is going to be very similar. The one thing that I will remind you of is that distance is equal to rate times time. So there are a number of the questions that involve this little formula. If you know the distance and the rate, or the time and the distance, you can solve for what's missing. And so a lot of times, if you need to know the rate here would be the distance divided by the time, right? And you can imagine how, if you didn't know the time, that was a variable, this could create a rational expression for you, right? Or the time could be the distance over the rate, right? Or some expression like that. So that's just a little note to look out or remember when you're doing these application problems. That's a fairly common equation for these. Okay. Well, I don't want to keep you here if it's, you know, if you feel good about these expressions. So we can, you know, it's a little early, but we've covered, I think, the most important things. So if you have some questions, you know, please stick around and we can go over some things. If not, you're free to go. I'll mark you down that you're here. You know, keep up with your work here as we move into our kind of last full month of the course. So don't get behind if at all possible, because there's less time to get caught up, right? We just don't have that much time left. So finish strong, as they say. Okay, I will